So next speaker is Mikyoung Jun, talking about statistical and machine learning methods applied to the prediction of tropical rainfall. Go ahead.
Thank you. Thank you. Okay, 1 second. Yes, so thank you so much for having me. And I'm a statistician. And currently, I'm at University of Houston Math Department. I joined this fall, but I was at statistics at Texas A&M for 15 years. And the work that I'm going to present is a joint work with Courtney and Saravanan at Atmospheric Science at Texas A&M. And recently, my colleague, Raymond Wong, joined our team to do more machine learning related research. And Jia Wang is the PhD student who actually does all the work that I'm going to present.
So just so you know, we can't see your presentation right now.
I'm sorry?
We can't
see. Oh, sorry. Yeah. I forgot to share my screen. Okay, so let me quickly do it. You can see it now, right? Yes. Sorry. Okay, so what I'm going to present today is basically some of the results of our ongoing work on understanding the rainfall, in particular the relationship with the rainfall and all the other atmospheric state conditions. And in the end, the ultimate goal is to improve the climate model in terms of precipitation, and I see some of the talks earlier are related to what we are trying to do here, but we are not there yet. And so far we are exploring various statistical methods and machine learning methods to learn about this so-called empirical relationship between the rainfall and the atmospheric state conditions. And so we are basically trying to predict rainfall from prior atmospheric state conditions, including temperature, humidity, and wind speed, and heat flux, and all those variables. In the work that I'm presenting today, it's based on the GPM satellite radar rainfall data. And we are classifying the rainfall into 3 different types: stratiform, deep convective, and shallow convective. And the atmospheric state data that we're using is from MERA 2 reanalysis data. So for both rainfall and the reanalysis data, we are working on 0.5 degree spatial resolution and 3 hourly temporal resolution. In the end, to put any relationship that we learn into a climate model, we need to do a global analysis. But so far, we are not there yet. And we are mainly focusing on 2 small Pacific regions, Eastern Pacific and the Western Pacific. It's relatively simple because most of the pixels are over the ocean. And so we are not currently worrying too much about the topography or land and the ocean and stuff like that, but we will eventually be doing it. So currently we are feeding our various models to the data from 2017. And then we are trying to predict over the entire year of 2018 and assess how each method does. A little bit more about the predictors. So as I said, our predictors are mainly the atmospheric state conditions. In this current work that I'm presenting today, we are mainly using a temperature and the humidity variable, but we have an earlier work that explored more variables other than temperature and humidity. And for the temperature and humidity, we actually have a data over 40 different pressure levels. And one of the main interests we have is how these vertical profiles of these atmospheric state variables affect the rainfall that we observe. So because at every pixel at any given time, we have 40 pressure humidity as well as temperature values at 40 different pressure levels, we tried various methods that people commonly do. We tried EOF. We also tried autoencoder to do the dimension reduction, which may work a little better than the principal component analysis. But in the end, what we found is that actually using the full 40 pressure level data for both variables give us a little better prediction results than those results with a number of EOFs or autoencoder. So we are now, I'm just presenting the results based on using full temperature and the humidity profiles. So one of the earlier work that's related to the work that I'm presenting today is also a collaboration with Courtney and Saravanan, and that appeared in 2019 Journal of Climate. So there, the question is basically the same. We're trying to learn the rainfall and relationship between the rainfall and the atmospheric state conditions. But the main difference is that there we only explored GLM method, which is more sort of traditional statistical method under some possibly parametric constraints. Another thing that's different is we only use the first three OFs of temperature and humidity, as well as wind speed. So we didn't really explore autoencoder or even using just full 40 pressure level information. Also, we use the 6-hourly trim data. And unlike in this current work, where we are actually using the full daily observations that are measured every 3 hours. Here we only used one time slot of 6-hourly to avoid some issues with the diurnal cycle. One big finding that we have in this work, which motivated the current work, is that just trying to explain the rainfall density based on gamma regression or any other regression, any other distribution that are commonly used in statistical literature for rainfall distribution is just not working due to this large amount of rain, which gives us this fat tail, we say, in the rainfall density. Just briefly about the methods that we used. The one method, as I said, is a GLM. And for the GLM, we use 2 steps. First, for the rain occurrence, whether it rains or not, we use the standard logistic regression. And all those atmospheric state conditions are used as covariates in the logistic regression. And once we predict where it would rain, then based on those predictions, we apply gamma regression to the rain amount, which is essentially what we did in the earlier paper. And in this current work, we added 2 more machine learning methods. One is random forest, which can be more flexible given that it's non-parametric and it can be nonlinear. And also we applied this neural net method, which in the end, we found out that which can be the most flexible method among these that we tried. Originally, before applying these methods, actually, at least myself and maybe Courtney, we had some doubts about the neural net, which may not be some kind of a black box that can solve every problem that we have. But the more we explore the neural net method, we are actually more convinced that it has more potential to explain this large rain amount, as well as the spatial map of the rain more accurately. So I'm going to show you some maps later. Just a little bit about the neural net we use. It's a deep feed-forward neural net. It's fully connected model. We are also doing this in 2 steps. One is for the rain occurrence and the other is for the rain amount. And we are using currently 4 hidden layers. We're not making it too deep. And one problem though with the neural net, I'm sure everybody's aware of, is it is really sensitive to how you initialize it. So we ended up trying multiple random initial points and basically take the best results that we can get. So just quickly here, I'm showing the results of rain occurrence prediction over Western Pacific. And just the numbers here are basically the percentage for each category. TN, for instance, means true negative, means there was no rain and we predict no rain, and so on. I'm showing it for 3 different rain types, and each column gives you the results from GLM, random forest, as well as neural net. And those bold-faced numbers are basically the true prediction. And the last 2 rows are basically the false prediction. And one thing you learn here is that there is no universal winner. Neural net tends to do better for the true negative cases, but GLM does better for the true positive cases, and so on. So overall, for the rain occurrence prediction, it seems like basically all of these methods work sort of similarly. For the rain density prediction is where we see the most utility of the neural net method. So as I said earlier, for the GLM method, we are just not getting the large amount of rain at all. And here what I'm showing is the density of the rain amount in a log scale. So the y-axis is in the log scale, just so that we can see it slightly better. And what you can see here is that the solid line is a true density curve, and then all those colored lines are the fitted curve. And we also included the Chem5 output here just for reference, which was given by one of the colleagues at Texas A&M. And what you see is just GLM, although it may get the density pretty well for a very small rain amount, it just doesn't get the tail at all. And oftentimes just the maximum amount of the rain that's predicted by GLM is much less than the actual large rain amount that we observe in the data. And overall, it's clear that the neural net is sort of the winner in terms of the rain density distribution prediction for all three rain types. This is more interesting to us, and now we are working on summarizing these results as a paper. Here, what we are showing is the annual rain map for each rain type, again, over the Western Pacific. And the top left corner is the true rain map, and then the other three are from GLM and the random forest and neural net. And just visually, when you see it, it's clear that neural net does provide the most sort of realistic a spatial map of the rain amount over this region for stratiform rain here. This is for the deep convective, and this is for the shallow convective. So overall, it seems GLM and the random forest just misses all the spatial patterns that we see, and it's very smooth compared to the actual data and so on. Okay, so I'm not sure how many minutes I have left, but I'm just going to wrap up. So what we are doing right now, the results that I have shown is over the Western Pacific, and now we're doing the same kind of analysis over the Eastern Pacific. One interest is to see how different or similar the empirical relationship is between the two regions and so on, which will be helpful, especially later when we go to the global analysis. And not just the annual rain map, but we are also checking and assessing the fits and the ability of the neural net method for predicting other aspects like MJO and diurnal cycles. And so far, what we see is that the results are quite promising, especially for the spatial maps. More statistical consideration that I have interest is here so far. Statistically, we were pretty simple-minded. We ignored all the spatial and temporal correlations that should be present in the data. We also did not really work directly to address the issue of spatial non-stationarity. Like for instance, over the land and the ocean, especially when we go to a more larger region, will be an important issue. But right now we are not really considering that at all. So those two are the stuff that we are planning to work on. And eventually, as I said before, we will eventually go to the global analysis so that we can incorporate into the cloud model. I guess I'll stop here.
Thanks. Great talk. There's one question in chat so far, and I'll let people post more. But Chandra's asking, what do you mean by rain density? Is it just the PDF of rainfall rate, or like an absolute rain rate?
Yes, it's just a PDF of the rain amount. Yes.
Okay, and then I had a question. So you have a pretty deep network, considering I assume you're just doing this on like an individual profile at a time, right? The 40 layers or the 40 pressure levels.
So the 40 pressure level is actually just the data.
Mm-hmm.
And so it's not the number of layers in the
yeah, sorry, I misspoke on that.
Right. So there we only have 4 layers. We don't. I mean, so far we are only using 4 layers, and it seems it's working pretty well. And so that 40 level pressure, I mean the temperature and the humidity given at all the 40 pressure levels, they are all fitted into sort of the model as a predictors.
And so I guess my question is, have you tried going towards something like a CNN or LSTMs to pull in either space or time?
So right. So those are all I guess, can be our potential future work. So far, we have been doing some kind of simple-minded approach with 4 layers only.
Okay, great. I don't see any more questions popping up, but if you have them, post them in chat and we'll be able to answer them there as well. So we can go ahead and move on to our next speaker then. Thank you.